Let's begin by understanding one of the most fundamental balance concepts in physics, the principle of moments. It tells us that for a body to stay in rotational equilibrium, the total turning effect in the clockwise direction must be exactly equal to that in the anticlockwise direction. If these moments are balanced, the object remains steady without rotating. Mathematically, we say sum of clockwise moments equals sum of anticlockwise moments. This principle is crucial in designing balanced systems like bridges, levers, and weighing machines. For a body to be in true rotational equilibrium, the net torque acting on it must be zero. This means it is either at rest or rotating steadily without speeding up or slowing down. If clockwise moments are stronger than anticlockwise ones, the body will rotate. So, balancing these opposing moments is key to maintaining stability. A free body diagram of a lever with balanced forces will help you visualize how this works. Now let's apply the principle to a simple lever. In a uniform lever, equal weights placed at equal distances from the fulcrum will always balance. But even unequal weights can be balanced if their moments are equal. That is, the product of weight and its distance from the fulcrum must be the same on both sides. For instance, a 1 kg weight placed 30 cm on one side can balance a 2 kg weight placed 15 cm on the opposite side. That's the moment balance in action. One of the most classic real-world examples of the principle of moments is a beam balance. When it is in equilibrium, the beam remains horizontal, which means that the clockwise moment produced by the unknown mass equals the anticlockwise moment produced by the known standard weights. The pointer stays vertical when the net torque is zero. This allows us to measure unknown masses with precision using the balancing condition. An important idea here is that it's not just the force, but also its distance from the pivot that matters. This distance is called the moment arm. A small force applied far from the axis can produce a strong moment. On the other hand, a large force applied very close to the pivot may produce a smaller turning effect. That's why tool handles are long, to maximize the moment using a smaller force. Let's solve a problem together. Suppose a 1.5 kg mass is placed at a distance of 20 cm from the fulcrum. We need to find the position where a 1 kg mass should be placed on the other side to balance it. We apply the principle, moment equals force times distance. So, 1.5 multiplied by 20 equals 1 multiplied by d. Solving gives d equals 30 centimeters. That's how far the lighter mass must be placed to maintain equilibrium. To sum up, the principle of moments ensures that a system remains in rotational balance when clockwise and anticlockwise moments cancel out. It forms the basis of many devices, from weighing scales to mechanical levers. The key takeaway is that both force and distance matter when calculating moments. Understanding this principle not only helps in solving physics problems but also in appreciating how balance works in the real world, whether in a playground seesaw or an engineering marvel.